Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Davy Kirkpatrick with us today. Hello, Davy.
Hello, Frank.
Thank you very much for getting to talk about your very lovely article.
Well, thanks for inviting me.
Sure. And Davy, what's your geolocation?
I am coming to you today from the Hollywood Hills in California.
I see a little bit of that Hollywood Hill trees out in the window there to the
It's the Italian cypress.
nice. Very cool. Is spring there yet? We got summer rolling?
I think we're still in winter as far as I can tell. We're still kind of cold, cloudy, a little bit rainy still.
Oh, okay.
I think we're going to skip spring and go right into summer, and it's going to be brutal. But
April 25th as we record this, people. Let's see, and I'm in Phoenix, and we are definitely warming up. I think we got very close to our triple digits yesterday, or Monday at least. So yeah, we're starting to warm up. So it'll be really good. All right, cool. And Davey, what do you like to do for research?
For research, I've been spending my entire career studying low mass stars and brown dwarfs.
That is awesome.
Very close to home, within a few tens of parsecs.
And that is going to bring us to this most amazing, I do have to say. Where's my screen share on this new one? Sure, here we go. Sorry, my bad. On this very awesome 93 page article, it is open access. It's the open access era, people. You can go grab a copy for free. Go get one. The initial mass function based on the full sky 20 PC census of about 3,600 stars and brown dwarfs. And Davey, take us away.
Okay, well, first I'd like to thank my co-authors on this paper, and you can see I have quite a few of them. There was a core group of us running from my name down to Stephen Scher, who's on the second line, were the folks who were primarily meeting every week. Some of us were funded via NASA ADAP grant to do this work. And Fede, who's the second author, and Chris, who is the third author, are the ones who, together with me, did all the deep dives into the NASA archives to actually find all the stars and brown dwarfs known within 20 parsecs. And Yadu, who's our fourth co-author there, is a high school student who did a lot of the simulations for the brown dwarf part of the mass function.
Wow.
He's a high school student up in Vermont, California. So we were very happy to have him on board because he did a lot of the really heavy lifting for that part of the paper. And then Jackie and Daniela and Stephen were also helping with various other tasks and just making sure we weren't missing anything obvious. So that was very good. And then there's a group of co-authors running from Kevin Apps down to, let's see, Aurora Kessely and Caselli. I think I just mispronounced that. I'm sorry, Aurora. They were helping out with other science aspects. There's some white dwarf experts on there, for example, because I had white dwarf things I need to do for this paper that I'm not really an expert on. And I'll talk a little bit more about Kevin, because he's sort of a special case here a little bit later when we go through the paper itself.
Okay.
And then going from Nikolai all the way down to, and these are basically in alphabetical order by last name, to Ziggy Wedricki, and I may be mispronouncing his name since it's Polish. Those are our citizen scientists who helped out with the paper. Talking a little bit more about the role that they played in doing this paper.
Yes,
and after Ziggy, going from Jose down to David, are some other primarily professional astronomers that helped me with mainly data collection and reduction and analysis for the paper.
Cool.
So that's how people got placed where they are, in case they were wondering.
Great shout out. Great shout out. Okay.
Sure. Okay. So yeah, let's talk about the intro here. So what is this about and why are we doing it? So the initial mass function. The initial mass function based on the nearby census is something I wanted to do ever since I was a tiny little grad student back at University of Arizona back in the late 80s and early 90s. And we couldn't do it back then because we just didn't have really any brown dwarfs to look at. And I really wanted to know how far down the mass function went.
Yes.
And, over the past 30 years or so, we've found lots and lots of brown dwarfs. We know they're quite abundant. But I really wanted to piece the whole thing together, the initial mass function, telling us what does star formation create from the highest masses all the way down to the lowest masses. How does it do that? How many objects in each mass bin does it create?
Yes.
And is there an endpoint? Is there some mass at which star formation is like, I'm done, I'm not creating anything lower than this?
Ooh, interesting.
That's what we really want to know. Okay. And what people have primarily been doing this in the past when looking at the initial mass function is looking at nearby star clusters and saying, okay, We'll
Uh-huh.
look at the nearby star cluster. We know it's at a very compact region of space. We can just point our telescopes in this area of sky over here, look at all the stars within that area, try to characterize them as best we can, and then figure out what the mass distribution of that collection is.
Yes.
Now, the problem with that is the nearest open clusters that you might be looking at in the galactic plane tend to be further away than the nearest stars.
Mm-hmm.
You also have a lot of reddening in the way. So, and there's a lot of reddening within the cluster itself. It's a fairly young cluster still. So you have to disentangle all that in order to characterize the objects.
Yes.
The problem with the open clusters is they don't hang around very long. They just eventually disperse.
Yes.
So you're looking at sort of a snapshot of what star formation is doing now, but what did it do in the past? So other people have said, well, we can look at globular clusters. Globular clusters are really old. They formed in the early epochs of the Milky Way, but they're even further away.
Right.
They're harder for the individual stars to characterize those.
Uh-huh.
But people have tried this, and they've gotten results out for the IMF based on both the open clusters and the globular clusters. And they see that surprisingly enough, despite the lag in time and the difference in metallicity between the two, that it looks fairly universal, at least for the stars.
Okay.
So star formation has a way of operating that it doesn't change as time changes or as metallicity changes.
Cool.
That's good for us because we want to look at the nearby sample and say, okay, if we look at this collection, think of taking a melon baller with the sun in the middle and just scooping out a 20 parsec radius of the Milky Way onto your table and just counting everything and looking at everything and saying, okay, what do we have here? This is a collection of what the Milky Way has formed over its lifetime.
Yes.
And we can see how that compares to the open clusters and the globular clusters. And we look at it in much more detail because these objects are very close. So we'll know whether we're looking at a single object, a double, a triple, quadruple, and so forth.
Yes.
And then we can characterize each individual component to figure out what its mass is so we can actually build the initial mass function. So that's the idea behind the paper.
I'm with you. Cool. Very good.
Okay, so let's scroll down to the second section here, and that is building the 20 parsec census. And you might think that in this day and age, when we have Gaia, which is this great European astrometry mission, that we just go to the Gaia database, we put in a simple query, we get our 20 parsec objects. We're done. Okay.
We're done.
Write a 93-page paper.
Yeah, exactly.
The problem is, and I really shouldn't blame Gaia for this, Gaia works at visible light wavelengths. And most of the stars are within 20 parsecs are easily visible by Gaia. So Gaia does a great job finding all the stars within 20 parsecs of the sun. Doesn't do so well in the brown dwarf regime because brown dwarfs are very cold. They emit very little light at the wavelengths where Gaia operates.
Yes.
So we have other surveys to do that part. So I realized a few years ago that because we had Gaia and we had WISE, which is the Wide Field Infrared Survey Explorer from NASA, to look at the long wavelengths where these cold brown dwarfs are more obvious and easily detectable, that we had a possibility of bringing these things together so we could build the entire IMF.
Nice.
The only piece that was missing was WISE is not an astrometric mission. We can't measure parallaxes with WISE. We get repeated observations, but the astrometry is of a low enough level that we can't really do parallaxes well for a lot of those. But at the time, we had Spitzer. So the Spitzer Space Observatory, Spitzer Space Telescope, was our follow-up instrument for WISE to actually get parallaxes for these brown dwarfs we were finding with WISE itself.
Okay.
So because all those three things sort of folded in nicely together, realized we can finally do this, something I've been wanting to do since I, again, was a tiny little grad student, and I could finally do it.
Nice.
Okay, so that is that's the idea here. So we went to Gaia first because that's the first place you want to stop, see if you can start building the 20 parsec census. And to cut to the chase here, when we finally got the entire table done, we realized that Gaia had 75% of the objects.
Okay.
It's missing a quarter. And you might say, why is it missing a quarter? Those are all brown dwarfs, right? It's like, no, there's some other things that Gaia is missing too.
Okay.
Gaia doesn't operate at the super brightest magnitudes because it saturates. So you're not going to find Arcturus, for example.
Okay. Yeah, sure.
Yeah, that's not very many objects, and clearly we know the really bright ones.
Yeah.
But there's some other objects that are just missing from the 20 parsec census in Gaia because it's an astrometric mission. It's trying to measure the astrometry, meaning the parallax and the proper motions of everything. And when you have a complicated system that maybe is a double, that's doing these weird little wiggles all over the sky, not just parallax and proper motion, but you've got the binary and imparting its own motion on that wiggle,
Yes.
may not be able to find a solution. So that object may just be missing,
Okay.
either from the catalog itself, or at least from the astrometric solution part of the catalog.
Okay.
So what we realized what we're going to have to do is dive into the literature, because people have been working on the nearby census for a very long time. So we've got a lot of things to pull out there from all the past folks who've been working in the same field. So that's what we started to do. And the rest of section 2 is just talking about the various checks we did, looking at other published dwarfs, looking at other published papers in the literature that have been looking for not only new objects within 20 parsecs, but also trying to characterize those objects within 20 parsecs.
Nice, very nice. Okay, recons. Yes.
Recons is one of the big ones that's helped out a lot. Yes.
Mm-hmm.
So if we keep scrolling down, let's see, we'll go on past this table, I think.
There's a lot of awesome tables in this paper, people.
And then we'll start at 2.1.2 there. Scroll back up just a hair.
Yep.
Okay, so we were able to flesh out as much of the stars within 20 parsecs as we could, but we still wanted to do an update on new brown dwarf discoveries within 20 parsecs, because those keep falling out in the literature, almost monthly.
Yes.
And we did a paper 3 years ago where we did a compilation of all the 20 parsec brown dwarfs, but the citizen scientists who are working on the Backyard Worlds project, which is another one of these citizen science Zooniverse projects, have been cranking out more and more discoveries, which we've been following up. Cool. And we need to do an update of that for this paper too. So that's why a lot of the citizen scientists are on this paper. That's one of the reasons anyway. They have found some of the new 20 parsec members that we announced for the first time in this paper.
Beautiful.
Yeah. And then let's see, we can keep scrolling.
Okay, keep my scroll going on this one.
I'm going to be scrolling on
newly discovered ones and
yeah, so the next, if we keep scrolling down, we'll maybe go to figure 1 now, Frank. And this is where we decided to dive into the NASA archives, which is really what an ADAP proposal is all about. It's digging into the archives and using the data in ways that the people who originally took the data may not have thought of.
There you go.
So we were going into every archive we could think of. We went into TESS, we went into COA, which is the Keck Observatory archive. We went into obviously looking for WISE data in more detail, Spitzer, things like that.
Nice.
Looking for objects we'd already tabulated as being within 20 parsecs and saying, are there any companions here that aren't marked anywhere yet that we really need to know about? Because we really want a complete census. We really want to know what is star formation created. So we don't want to miss anything.
Yes.
And this is 6 examples of things where we found something for the first time just by looking in archives. It's like, okay, the star in the upper left there is a big bright A. Very tiny in B is sort of an orange looking brown dwarf companion to it that no one had noticed before. And one of our citizen scientists pulled that out.
Nice, congratulations.
He decided he was just going to do a visual search of everything within 20 parsecs and see what he found. And those 2 things were co-moving together.
Nice. Yeah, yes.
Okay, so we can keep scrolling past this.
Very good.
Talk a little bit more about sort of the buildup of creating the census in the first place.
And checks.
Yeah, we did other checks against other literature.
Yeah, that's a good thing to do.
And then we created our big table. And the big table is the next table that you'll run across here. This is the 20 parsec census. It's got rows and rows and rows and columns and columns and columns.
It's fantastic.
And the reason we did this was for every system and every component in the system, we wanted to collect a lot of data on it so we could characterize. Because remember, the eventual goal of this is to actually get a mass estimate for every single object within 20 parsecs. And this was a lot of work.
Just to be clear, people, this is a machine readable table. So this is just the headers to it. The actual table is not here. The actual table is available right here, machine readable form. So you can get it.
That's it. Okay, so we can keep scrolling here. Since this is a 93-page paper, we'll have to
have some pace here.
Yeah, we'll have to skip over some details. But...
Yeah, if you want to check.
Okay, then we come to 361.
Okay, yes.
Okay, 361. I mentioned that we have this table now that is essentially the 20 parsec census.
Awesome, congratulations.
And we pulled that out of certain papers from the literature. We've certainly not at this point looked at everything because it would take you a lifetime to look at all the papers in the literature. And I decided, because I didn't want to go crazy myself, I needed some help doing this part where I needed to dive in and look at the literature in more detail.
Okay.
So as a sort of a adjunct project on the Backyard Worlds team, we decided to set up something called the Stellar Ambassadors Program.
Okay.
And for any of the volunteers who wanted to become a Stellar Ambassador, they would get assigned an ambassadorship to 12 different systems within a 20 parsec sample.
Okay.
They're going to be Earth's representatives to these systems.
Okay.
And you know, the Earth Coalition is not going to just send you out and you not know anything about the systems there because you're representing Earth, but you don't want to look stupid to the systems that you're now representing
Oh,
Earth.
fine.
So the idea was for each ambassador to go off and look in the literature and say,
Good.
well, you need to learn about your 12 stars.
Yeah.
And
Great.
you know, if you're ambassador at Alpha Centauri, you want to know at least that there's 3 objects in the system. You don't want to get there and look stupid and say, there's a Proxima? Really? No idea.
Very good. Yeah, that's one way to get to the literature is parallelize it.
So when we set this up, I knew, you know, there was a very high likelihood that what we would get back from this is going to be sort of a heterogeneous mix of things because each citizen scientist has their own way of doing things. Some people prefer doing programming to actually looking at the literature, so they're going to go off and look at archives.
Right.
Other people are going to do deep dives into Wikipedia. Others are going to do deep dives into SIMBAD.
Yeah. Okay.
The point was not for any of the citizen scientists to really be complete in what they were doing. What I was looking for was which references kept popping up over and over and over again. I knew when those kept popping up over and over and over again, those are the ones I needed to look at first.
Okay.
So that's how we did this. So in fact, there were quite a number of papers that are characterizing exoplanet systems, for example, where they needed to know more about the host stars. And well, that falls in perfectly for what we're trying to do here because we want to know more about the number of objects in those host star systems.
Yes. Okay.
Okay, so let's see. Why don't we scroll to the next page? So, let's back up just a little bit. I want to talk about 363 here. So,
Yeah. Catalog.
when we had almost gotten this entire thing done, and I thought, okay, I've finally got this as good as it's going to get. I heard from Kevin Apps, who's now one of my co-authors, and he calls himself an independent scholar in the United Kingdom.
Okay.
And he is someone who he does have, I think, a master's degree in astronomy and astrophysics. But he decided not to pursue that as a career. He does something else now. But he's always been fascinated, particularly with the nearby sample. Well, unbeknownst to me, until he got in touch with me, he's been keeping his own list of nearby stars. He goes through every day's worth of astro pH and adds to his table. And I went, oh, okay, we have to collaborate, please.
Nice find, but
yeah. So at this point, I decided, don't give me your table. Let me just send you a summary of what I have. And we did it in, one block of RA, and we would continue on throughout the whole 24 hours of RA. So the objects I have, and here's what I think their multiplicity is. I think this one's single. I think this one's double, et cetera, et cetera.
Cool. Okay.
And he would come back and say, okay, we disagree on these 6.
Okay.
So we'd go off and say, okay, I have a companion here that you don't have. Did you miss this? He's like, nope, it's been discounted. Here's the paper that discounted it.
Okay.
Or in some cases, I'd say, you don't have this brown dwarf. He's like, has that been published yet? And I'm like, well, no.
Okay.
That's what we don't know about it. So this was a great second check.
Yeah.
So I have a lot of added faith now that what we've done is pretty close to right. We may have missed a few things, but I think it's pretty good, pretty solid.
But was a very nice independent check verification, double nice.
Absolutely. I was so glad he said something because that made me feel a lot better about the 3 years I put into this. Okay, so if we scroll down to that next figure, this is just an example of what one of the systems would look like in the table. And this is a system that has 5 components. It's 2 close double stars, and it's got a far-flung brown dwarf companion.
Yep.
So I would have a line in the table for each one of these individual components, as well as, the B system, which is composed of 2 components, and a line for the A system, which is composed of 2 components, and then a line for all 5 at the top. And the reason you want to do this is there are some surveys that have poor resolution, so they may have combined photometry of all 5 together, and you want to know that.
Yeah.
There are other surveys that have exquisite resolution. They may have independent photometry of all 5 components, and you would want to label that as such in the table.
Definitely.
And this is important a little bit later.
Okay.
Okay, so let's scroll along. Okay, so masses is what we want to eventually end up with. We think we have all the individual components, at least as well as we can do, identified. Well, we want to use direct mass measurements wherever we can,
Yes.
because those are, the truth.
The truth, yep.
Really only want to have to estimate masses when we don't have any other option. So this section is just basically reminding everyone, how do we get masses for stars? What are the various ways we do that?
Okay.
And you can do that for multiple systems. You can also do that for some single systems. So for the multiple systems, it's usually you have visual binaries where you're looking at the orbit on the sky.
Mm-hmm.
You have spectroscopic binaries that also have eclipses. So
Yes.
there the masses directly. And a few other methods too, like astrometric binaries, where you can get the mass measurements directly.
Yes.
And there's also another two other categories, and one is accelerators, and that's where you go off and you look at an object at one epoch, and you study it again in a second epoch, and you say, okay, I see there's a proper motion on the sky, and I can see the proper motion vector going this way. And then you come back later after a few years and you measure it twice again. And you're like, well, now the proper motion is going this way. And how could it be doing both at the same time? You realize, oh, there's a second component there.
Right.
That I'm not seeing. And what I'm seeing partly is the orbital motion affecting my proper motion measurement.
Mm-hmm.
And if you look at those long enough, then you can get the mass measurements of the individual components as well.
Yep.
And then another way, especially for the white dwarfs, because they are very compact, and this is a larger effect that you can actually measure, is getting the gravitational redshift. And for those, I lump those into the multiple category, because you've got the gravitational redshift, but you also have the radial velocity on top of it. And if you don't know the radial velocity independently for the white dwarf, you don't know which part is radial velocity and which part is gravitational redshift.
Okay. Yes.
But if you've got a double system and you can measure the radial velocity of the M dwarf, for example, then you can apply that same radial velocity to the white dwarf and say, what's left over is the gravitational redshift. Now I know the mass of the white dwarf.
Gotcha. Cool. Thank you.
Yeah. And then for single objects, you've got gravitational lensing.
Mm-hmm.
An object, and you have to get really lucky here, obviously. Your brown dwarf or your M dwarf or whatever just happens to go in the line of sight between you and a background object, and you see effects on the background object, the brightening and the astrometric displacement that you can measure the mass of the lens by.
Mm-hmm. Which is
And there are things that pulsate and have other oscillations relating to convection. You can actually measure masses that way too for just a single object. So we're using all of these methods where we can to set up the direct measurements for as much of the sample as we can.
Cool. Very cool.
Okay, so section 5.1 is getting back to the accelerator part. So it turns out there are many ways you can do accelerations depending upon what surveys you have available. And there are people who are looking at the Hipparcos proper motions versus the early Gaia proper motions and finding things that are clearly accelerators.
Okay.
And that may be all the information we have right now. We know there is a second, maybe even a third component in that system, but we don't have enough data yet to characterize what it is.
Okay.
So this is a big uncertainty in building the IMF, because we know there's a companion there, but we just can't characterize it yet.
Okay.
And there are other people who've gone off and said, okay, instead of using Hipparcos and Gaia, I'm using early digitized sky survey plates plus 2 mass and follow-up to do a second epoch, and finding that, yes, the proper motions on those don't align either. So we have a whole list, and I've compiled that in the next section, of objects within 20 parsecs that we believe, and that's table 5 and I think table 6 as well, that we think have other components that just need more follow-up.
Okay. Okay.
Yeah.
Very cool.
Okay, so we can keep scrolling here.
Well, here's the
other sets.
Yes, so the 20 PC accelerators. Okay. Very good. Nice. Nice. Okay, that's a complete table. Multiples with large RUE.
Really nice. Yes. So Gaia also provides their 5-component astrometric fit, which is just basically saying, okay, I'm looking at the astrometry, the measured positions of all these objects, and I'm going to assume that I'm measuring for an RA and a deck at time t0, whatever I pick as time t0, a parallax and a proper motion in RA and a proper motion in deck. Those are my parameters. And sometimes when you look at the sequence of positions for an object, you'll say this fit is just lousy. And it's not lousy because the uncertainties are bad. It's just like it just doesn't fit.
Right.
There's a second component in there, which is adding more wiggle on that because you're seeing partly orbital motion right on top of the thing that you're actually trying to measure parallax or motion. So those are labeled as things with high RUI, which just means the renormalized unit weight error, which is just telling you how bad the fit is and with high parameter fit. And most of those are probably most likely going to be binaries we don't know about yet either. We just need more data again to characterize those. And you can see there's quite a number of those as well.
Yes.
Yes.
Okay. Very good.
Yeah. So that's table. Yeah.
Table 8.
Okay. So that's just the one big caveat here is that, clearly more work needs to be done on the 20 parsec sample. Even though it's so close, we still have a lot of work to do.
We'll come back to that. Okay.
Yeah, we'll come back to that. Okay, so let's keep scrolling. And okay, here's where we are finally going to get into looking at the table we've created in all photometry we very carefully collected to see, is there anything else odd we need to know about before we start estimating masses for the ones that don't have direct mass measurements?
Yes.
So I think if we scroll down to the next set of plots.
Okay, let's go down to CMDs. There we go.
So this is the first set, and these are just showing absolute magnitudes as a function of spectral type in this first set. And there's a color bar at the top, which color codes the spectral types. Okay, curious. And let's see, Frank, if we can go to the next one, I'll just show that one. And that is,
5, yes.
These are absolute G, which is just the Gaia main band, the broadband.
Oh, what was
versus various colors.
The other one is various bands. Okay.
Various bands, yeah. And then if we go to the third set.
Okay.
The third set is showing various absolute magnitudes versus the J minus W2 color. And the W2 color is the 4.6 micron band from WISE. And Frank, if we could blow up the one in the upper right-hand corner, that's the absolute J magnitude versus J minus W2.
Yes.
Okay, we're looking at this and saying, okay, we see a nice main sequence there going down from basically the A stars down to, the early L dwarfs. The early L dwarfs have a kink and come back to the left, and then they hit the T dwarf sequence and start going down to the right again. And you end up in the Y dwarfs way down on the lower right-hand corner.
Yes.
And then off to the left, there's a whole group of little white dots, and those are the white dwarfs.
Yes.
Obviously, we have white dwarfs in the sample too. Quite a few of those, in fact. And those are objects that used to be the most massive representatives in the 20 parsec sample, except they are now more evolved. And we'll get to that in just a second too.
Okay.
Purpose of plotting up this diagram is to see if there's any weird outliers that we want to know about, because weird outliers could be indicating one of a couple of things. One is maybe there's a binary there I don't know about. So the photometry I've got listed in the table, because the object is sitting above the main sequence, is actually double, and no one ever noticed that before. But we're seeing it now because the absolute magnitude is too bright. There could also be things where we've got an object of a weird metallicity, and it has an unusual color.
Yeah.
Or its absolute magnitude. And then we may have to be a little careful about assigning a mass estimate to that because it's a different kind of beast.
Yeah, that gets into the whole merger game, right? So what if all you see is the result of the merger?
And then you may have some things that are even evolved stars off the top of the main sequence that, are going into their giant phases. And you want to be a little bit careful about estimating masses for those too.
Indeed. Yes.
So be careful when you take colors. You want to make sure you got the color of the right thing before you start estimating your masses. So that's just a reason we did these plots, is to see if there are any other special cases we need to be aware of.
Yeah, well, it's an interesting kink here as well, right?
Yeah, because the L dwarfs get really dusty, and then the dust clouds start to part and fall out into grains, and you get a clear atmosphere again, and then off you go on another sequence.
Yeah, cool.
Yep.
Good.
Okay.
All right.
So yeah, we'll zoom back out and keep going here.
Okay, we'll leave that one there. And figure
we'll go past that one too. And then this is just another set of absolute magnitude versus color. And this is color versus spectral type.
Yes.
Okay. And then the section here is just looking at all the outliers and trying to figure out what they are. Okay. I won't go into any detail there. And these are just more.
Let me just ask, out of the 3,600, how many outliers were there total?
I'd say a few dozen.
Okay.
Really not that many, but enough to make me worry.
1%?
I worried for 3 years. Yeah, right.
Well, I don't want to stop you. Keep going. But you know,
I felt good when all this was done. It's like, okay, I don't think there's anything obvious I missed that the referee will say, well, didn't you consider this?
you don't want to say no to that.
Okay, so let's see. Let's keep scrolling here.
Nice.
So we've characterized these weird ones, and now
Masses.
we get to the part where, okay, let's estimate masses for everything else.
Yes.
Okay, as I mentioned, white dwarfs are involved. And this is supposed to be an initial mass function. And the initial is a very important word here.
Yes.
We want to know what star formation created, not
Mhm.
what it ended up with after the stars lived out their lives, whatever that means. So for the white dwarfs, we know they're evolved. We know they have lost mass somewhere along the way. And we want to be able to look at their current state to figure out what their initial state was. So
Yes.
what mass were they born with?
Yes.
So that's the whole point of section 6.1.1 here, is looking at the white dwarfs and saying, okay, how do we do this? And the white dwarf experts have, spent a lot of time trying to do this kind of thing where they convert final mass into an initial mass. And they have these relations that are based on looking very carefully at clusters of known age, and they can do this pretty well. Now, the uncertainties in going from the final mass to the initial mass are kind of large, but that's okay. I mean, we can deal with that. It's the best we can do. We're not going to be able to do anything more than that. And just as an aside, when we did the final mass to initial mass relation to get what the initial masses were,
Yes.
the most massive object within 20 parsec was around 7.3 solar masses, something like that. So just below where you start getting neutron stars.
Yes.
So the highest mass star that we would have seen had we had a pristine, just formed sample within 20 parsecs would not have created anything like a neutron star or a black hole. So we should not expect any neutron stars or black holes within 20 parsecs, and we don't see any.
That's kind of good.
That's kind of good, yeah.
At least for us.
Just in case you were wondering.
No, but that is interesting, right? I mean, there are no neutron stars or black holes we know of within 20 parsecs. That's interesting. Experimental. Very good.
Okay, so if we scroll down to the next section, so we've done
Dwarfs.
dwarfs.
And then here are the various methods. This is good.
That's right. These are all the white dwarfs within 20 parsecs, and the ones in bold in that middle column are the ones that have direct mass measurements, and the ones in the normal font are the ones where we had to estimate.
Okay. Okay.
And again, that's for their final masses. We still had to use those to get the initial mass.
Yes. Yes. Okay. Very good. That's a cool table.
So we're continuing to have fun here. We've gotten our white dwarfs dealt with.
Good. Okay. Those are the white dwarfs. Now we got some other things to worry about.
Okay. Now giants and subgiants. So the giants and subgiants, there are quite a number of those who have either direct mass measurements because they're in a double system.
Yes.
Or they pulsate, so we can get from astroseismology their masses.
Mhm.
There are much more where we didn't get lucky in either case, so we don't have those methods available. So you basically have to go to the evolutionary tracks and plot things up. And on those diagrams, I was just showing color, and color magnitude diagrams to see what they are. So that's where the masses came for those. So, and we think these are not terribly evolved giants and subgiants for the most part. So we think the mass loss they've had so far is negligible. So their current mass should be very close to their initial mass.
Okay.
Yeah.
Okay.
Oh, yes.
Sorry. Yeah. Yeah. Very good. Citizen. Okay, cool. Very good.
Yeah, you may see some old friends in there.
I do. Okay, I was just saying hello to them.
Yeah, it's always good to do that.
Yeah, and
and then the
brown dwarfs.
Yeah, the last one's the brown dwarfs. So the brown dwarfs have a sort of a unique problem in that you can't look at their colors or spectral types or anything and map that directly to mass because they do not have thermonuclear fusion in their cores for any sustained period of time. So they just keep cooling.
Right.
So the only way you can know what their mass is, if you know what their temperature or the spectral type is to know when they were born.
Yes. Okay.
And for most brown dwarfs in the solar neighborhood, you have absolutely no idea how old they are. So it's like, oh no, have we hit a wall here? No. What we're going to do instead here is look at the distribution of effective temperatures for these brown dwarfs.
Okay.
So instead of looking at the mass function, we're kind of looking at the current effective temperature function.
Yes.
I'm saying, okay, I can build that empirically with my data.
Yes.
I can also go over here and ask my favorite high school student, can you run these simulations for me and look at for various forms of the mass function, for simplicity, we considered a bunch of uh, power law mass functions and said, okay, let's assume a bunch of power law mass functions. Let's also assume that we have different low mass cutoffs for the IMF. We can pick 10 Jupiter masses, 5 Jupiter masses, 1 Jupiter mass, whatever.
Sure.
We can also pick different star formation histories for the Milky Way and say, okay, maybe it's been continuous. Maybe there's been a few, mergers, satellite galaxies and things. So there's been some bumps and wiggles along the way, that kind of thing. And we can take those estimates and run them through evolutionary models to say, okay, with this formation of brown dwarfs, we should have this current state of effective temperatures. And we can do that for a giant suite of models.
I'm with you.
And also a bunch of different evolutionary codes just to see how much they differ amongst themselves.
Yes.
When we do that, we can actually compare our effective temperature distribution to the simulated distributions to see which is the best pairing.
Okay.
And we'll do that a little bit later in the paper, but that's coming up.
Yeah, good. That's a nice lead. Okay.
Yeah. Okay, so we have a few other complications. One is youth. There may be some very young objects in the solar neighborhood that also we should be a little bit careful in estimating their masses. And fortunately, there aren't very many of those. So if they're skewing the results, it's not by a very large fraction. So, but we did identify what those young objects would be and the ones that are skewing the results here.
Yes.
Just in case anyone wants to go off and do additional work.
Yes. Oh, you're more than welcome. You'll be on the next paper.
And then there's a second category here, which is, are there objects of really low metallicity? So these are either, kinematically old objects, or they're just objects that have, far different from solar metallicities that we need to be careful when we're converting colors and spectral types to mass estimates.
Metal's
and
cool.
Again, there are very few of those as well. So it's a very small percentage. But again, we tabulated them here in case anyone wants to look at the details and try to do a better job.
Ooh, here we go. 2 diagrams.
And it's, so we got those guys labeled too. And I'm going to, I think, skip section 6.2.3 just from a time consideration here. So
we're doing great. We're doing great. No
okay. Go on to the next part, which I gotta remind myself.
Okay.
That section that I'm skipping is really making sure that things that people label as planets are not thrown out of the sample if I think they might have formed like a brown dwarf, because we're two competing definitions of brown dwarfs. So one based on formation, one based on mass. And we care about the one based on formation.
Formation, yes. When it was there. Okay.
Okay, so now we're getting into the mass estimates. So we detail how we do the mass estimates for all the remaining objects in the sample. And we use primarily things that are already published in the literature. In some cases, we had to come up with our own new relations. And this is in figure 12, just showing one of those, which is an absolute G magnitude versus mass. So if all we have is an absolute G magnitude for one component in the system, we can at least get an estimate of its mass, for example.
Yes. Okay.
And there's things that, Gaia's found for the first time. So we have to use this relation, for example. We have no other data.
What else?
Yeah.
Okay. Gotcha.
And so we can also scroll to I think it's figure 13, maybe.
Let's see. Objects of the main sequence, functional form. 13 is
13 is just showing an example of how some of the various mass estimates compare.
Okay.
And they compare fairly well. Everything should fall along the dotted cyan line there, but there are some places where different methods sort of start to veer off from the other, and we'll get to that in a little bit too. This is an area where we could use some help. So these are just two different mass estimates from two different methods and plotted, and you're just looking at the difference between the two estimates. But yeah, the one I wanted to show is this next figure.
Ooh, yes.
And this is just the adopted mass from we found in the literature versus spectral type. And the thing to point out here is, even though I've been working on low mass stars and brown dwarfs my entire career, this still kind of surprised me when I plotted it up as to how steep that function is in the M dwarf regime, particularly from M0 to M5. You're
Uh,
covering a lot of mass. You're covering from 0.6 all the way down to, practically, 80 Jupiter masses, which is the stellar substellar boundary there.
right. Wow.
And when people say, most of the nearby stars are M dwarfs, that's why, because that's where most of the mass is.
Yes, yes. Wow, that's amazing.
But it's also so steep that it makes you worry if you've really estimated the masses super well there, because it is a very steep function. If all you have is spectral type to go on, just be aware that your mass estimate probably has a pretty big uncertainty on it.
Because it's so steep there. 1, 2, 3, 4. Yeah, broken power law, 4 or 5 components. 4.
Yeah.
Yeah. Okay.
Okay. Okay.
Cool.
So now we're going to finish the uh, analysis of the brown dwarfs here. So brown dwarfs have a few more complications we need to be aware of. One is that even though when Gaia is looking at the stellar part of the sample, it's not going to be magnitude limit, because out to 20 parsecs, we're easily seeing all of the stars by
Yeah.
Gaia. Gaia can go much further out than that. So there's no worry that Gaia is incomplete within 20 parsecs.
Okay. Agreed.
Eyes, however, will have some problems, because even though it's working at the right wavelengths to pick up these really cold objects, it can't necessarily see the coldest ones out to 20 parsecs. It's just doesn't have the sensitivity. I would love if it did, but it doesn't.
Okay.
And we found out that to the late T's, we're maybe only complete out to 15. And for the wide dwarfs, it may be only 10, 11, 12 parsecs, something like that.
Okay.
And the way we judge that is by doing this, what's called a V over V max test, which was Martin Schmidt back in the 60s or 70s came up with this as a way to judge your completeness in a sample. And what you essentially do is you have a volume, and you say, okay, within this volume, I want to know if I'm really complete or not.
Okay.
So what you do is you take the subvolume within that should be half the size of your total volume.
Okay.
And then you count up the number of objects in that half volume and compare that to the total number of objects in the full volume.
Yes.
And that ratio should be 0.5. You should have half as many in the little as you have in the full. And when you start to deviate, and you can try this for, you can keep going out and making the volume bigger and making the inner volume
3/4, where it may be.
Right. And when you do that, you'll eventually see that, yeah, I'm starting to get out to the regime where my fraction is falling off 0.5. I no longer have twice as many objects in the full volume as I have in the little inner half volume.
Okay.
That's a way for you to be able to judge your incompleteness and where it happens. And that's very important. You want to know where it happens. Yeah. And this is what we're doing here. We're just dividing the brown dwarfs into various temperature bands and looking at completeness.
And there's the 0.5 line.
And see, we're doing 0.5 pretty well for the hotter things. And then when you start getting to the colder, it's like, we're falling below 0.5. Uh-oh.
Yes, barely there. Oh, even here, getting below.
Yeah, but it's still within sort of the uncertainties of what we expect. But if you look at the points on the right, you're seeing that we're starting to dive below the 0.5 value a lot.
Oh, so I missed this whole thing. Okay. Yeah.
Yeah, the 300 to 450 Kelvin band there, for example.
Ooh, yikes.
To fall off at about 11 parsecs or so.
Yeah. Okay. And the really cold ones, well, we don't know.
Yeah, well, we only have one. It's
right.
hard to... He's an anomaly.
Very good. I like this. Okay.
Okay, so this is a way just of knowing what we can count and what we shouldn't be counting in our parsec.
Yes.
So we need to get the space densities right to do this correctly. Okay, and if we, let's see, scroll down to the next plot. There's another way you could be incomplete too. It's not only the fact that you have a magnitude limited survey, but you may also have incompleteness in the galactic plane, because you've got very busy background. Okay. Trying to find very cold, very dim objects against a very busy and then bright background. You may be missing things. So we also look to see if there were objects, if we had sort of a deficit of objects along the galactic plane. Yes. And for T dwarfs and Y dwarfs, we do. So we have to correct for that as well. It's only, 10 to 15% error, but it's something that we need to account for.
T dwarfs only.
And it's not so obvious on these plots. You have to sort of bend them up very coarsely to see it.
What is the, let me just ask, what does the gray circles mean on these?
I think those are the new additions. So since our last paper, which was 3 years ago, those are all the citizen scientist discoveries.
Yeah. Okay, good.
That's a great question. Thanks for asking.
Yeah.
Okay.
Got it. I'm with you.
Okay, and then let's see, we keep going. So I think the last step here is to actually look at the space densities versus Yadu's models.
Yes.
And when we did that, we found that the best fit is really an alpha of about 0.6.
Oh, these are the T-effective distributions. Okay. Okay.
Yes, these are the T-effective distributions and the space densities as the y-axis, yes.
Okay. I'm going to zoom out here so I get a global first. Okay.
Yeah. And we could not really distinguish between the low mass cutoffs. Those are the three different colors in each panel there. We really need objects that go colder than the ones that we currently have to figure that out well. But we know it's somewhere probably below 10 Jupiter masses.
Very
Star
interesting.
formation can really create things fairly low mass, and it's continuing to create things down below where we can actually currently see.
Mm-hmm. Mm-hmm.
Okay.
In here. Okay.
So next plot.
It's growing. It's growing. Okay.
Oh, we're going to skip this one actually because this is some more details I don't need to go into. So it's this plot is actually showing for each one of those temperature bins we were looking at before, what this predicted mass function would say are the masses of the objects in those bins.
Yes.
And notice when you got the hotter objects are all kind of concentrated on one mass, but as you go to the lower and lower, sorry, the fainter
spreads,
lower and lower temperatures, you get a larger spread.
Yes.
Until you start getting to the very low temperature objects, and then the mass distribution starts to tighten up again because you get really low masses there. But the upshot of this is that we can use these estimated masses to fold this back into the IMF.
Yes.
So those are our estimated masses that we're going to use. We can't do it per individual brown dwarf, but we can do it for the distribution brown dwarf.
Okay, good. Good. Okay. I am with you.
Okay, excellent. Okay, here is the money plot at long last.
Drum roll, drum roll.
Okay, so this is the IMF from all this work. So in the upper left, you see the full IMF going from 8 solar masses on the left down to 0 on the right.
Yes.
And this is just plotted against the number of objects, or if you want to think of it as a space density, is the y-axis on the y-axis there. Okay, and I've subdivided this plot in the upper left into 3 other mass regimes so we can see the details.
Okay.
And on the upper right, we see 8 solar masses down to 1.5.
Okay.
The lower left, we see 1.5 solar masses down to 0.4.
Yes.
And in the lower right hand, we see 0.4 solar masses down to essentially 0.
Okay.
And let me explain what the colors are on this.
Yes, please.
So the blue histogram that you see there is the histogram of the estimated or directly measured masses for the stars in the sample.
Okay.
And if you zero in on one of those peaks in the blue histogram there, and if you looked at the individual stars in it, you might see, for example, there's an object that has an estimated mass of 0.4 solar.
Okay.
It might have a very tiny uncertainty on it, 0.001 solar masses or something.
Yeah.
And there might be maybe another mass, another object in that bin that's also 0.4 is its mass estimate, but it might have plus or minus 0.2.
Oh.
Is its uncertainty.
Right.
Does it really belong in that bin or not? Or is it really should be shifting higher or lower? So what we did was that we did Monte Carlo simulation here.
Okay.
We took those uncertainties and said, okay, let's run 10,000 simulated distributions of this particular set of objects we have and see what that distribution would look like and what the uncertainties in that distribution would look like if we just folded in all those uncertainties on our estimated and measured masses. Good. And what you get out when you do that is the black points with the error bars here. Okay, so that's really what we're trying to fit to.
Yes, exactly. Okay.
And the bits that we've tried, what we decided to do was just stick with a power law mass function and tried to fit as few pieces as possible to make the shape work.
Okay.
So at the highest masses, what we did was, it's like we really can't do better than saltpeter because people have been measuring the high mass stars for a long time. So we just fitted a saltpeter slope to that.
Yep.
What you see is the magenta in the upper right-hand diagram there.
Magenta.
And then if you look at the lower left-hand diagram, it continues on with a saltpeter slope, and then there's a little kink at about 0.5. It get a little bit shallower for a bit. And that's the alpha of 0.3 that people have been is it one? I think it's no, not 0.3. I've got to go back and look at my values later in the paper now, but it gets a little bit shallower down there.
Yes, and then it increases.
And then you get to the plot in the lower right, and you see as we're going through sort of 0.25 to 0.1 or a little lower, it gets shallower still.
Yes.
So the third part of the mass function there, and then it takes off again, and the brown part zooms up.
Boom.
We have a 4-part power law that seems to fit. And you notice there's bumps and wiggles in the in the black distribution there that, some of that is artificial, and I'll talk about that just briefly in the next figure.
Okay.
And we'll zoom in on that bump that's right there at about 0.6 or 0.5
Okay.
in the lower left-hand panel. So if we go down to figure, we go down to figure 21, that's shown again here in the left-hand panel.
Okay.
And that's a consequence of my stitching together two different estimate techniques.
Okay.
If I decide to stitch those together at a different mass because they have some overlap, I get the plot in the middle, and you see now the bump is moved down.
Yeah.
That bump is artificial. We know that's artificial.
Okay.
On the far right, I can just say, okay, I'm not really sure about these estimates, so I'm going to inflate the uncertainties. I can get the bump to basically go away, not entirely. So what that's telling us is that, our estimates are probably not quite as good as we think they are, and we really need to put a higher uncertainty on some of these mass estimates before doing the analysis.
Right, particularly when you start blending, right, different data sets. And
right.
Where you choose to blend, right? Yeah.
Exactly. That's exactly
right. Yes.
Okay. So that's just a cautionary note. Okay. So let's keep scrolling here.
Piecewise, we're going to get to the fits.
Yeah, we're going to go down to the bottom of this page, which is where we have. So there's my alpha values. I guess they're actually on the next page, the alphas themselves.
Let's figure
in the text part. Yeah, keep going just a little bit more.
Keep going.
There we go. So 2.3, 1.3. Yeah, I was thinking saltpeter gamma rather than alpha. Sorry about that.
There we go. That's okay.
Saltpeter alpha is 2.3. The next one's 1.3. Then we flatten up to 0.25 and then go up again 0.6.
And that's right. That was what we saw in the figures.
Yeah, that's exactly right.
Exactly. Very good. Okay. I'm with you. So we got that was the fun word used in the abstract. Quadrupite. What was that?
Quadripartite.
Thank you. I hadn't heard that word before. I had to look that up and go, oh, okay.
I try to use one weird word every paper.
You won on that one. You got me. I learned something. Sorry.
Okay. In figure 22, which is the last one in the main text here we're going to talk about, is actually comparing our results, which are the ones shown in the mustard colored line, to some other results from previous literature. And you see at the highest masses, which is shown in the left-hand diagram and the middle diagram, they're not too bad. I mean, things fit pretty well because we've known what star formation does at the higher masses for a long time. But then you go to the right-hand panel. Yikes. This didn't have that right at all before.
Yikes. Correct.
We were predicting way too many low mass stars and brown dwarfs, at least depending upon which model you pick. And now we know closer to what the truth is.
Very good. Very good. Ooh, wild. Okay.
Yeah. So why don't we scroll to some of the conclusions here? So there's 2 or 3 really important conclusions from this.
Very good. Okay.
First of which is, since we think we do have mass function that is more or less universal over time, that what we're seeing as this 4-part power law is actually telling us something about the physical processes that occur in star formation itself. So we think there are these different regimes where the process changes. It's a little bit different from one mass regime to the next. And we've got to figure out theoretically and maybe even observationally what those processes are. Another takeaway from this, and let's see, I think we'll go to point 0.3 here, is one of the values that the theorists really wanted for me from this was, what is the average mass that's created by star formation?
Okay.
And our results say 0.41 solar masses. And the ones who've written back to me said, well, we've been assuming 0.5, so we're too far off all this time. But there's a caveat here, and the caveat is we haven't seen all the brown dwarfs yet. We know that they're lower. We've got more brown dwarfs out there, and we need something post-wise to find them.
Right.
So if we assume that 0.6 power law keeps going all the way to 0 masses, it could be that the average mass that star formation produces is as low as 0.34.
Yes.
Could be the alpha gets even steeper down there. Who knows? And that could be even lower number. So
Okay.
jury is still out, as they say.
TBD.
Okay. And there's one other thing I wanted to mention. That is, if you look at the number of stars versus brown dwarfs, we now think, based on the census, that that ratio is 4-to-1. So there's 4 stars for every brown dwarf.
Okay.
And
Okay.
just a few years ago, that was more like 6 or 7. So we have been finding brown dwarfs like crazy. And again, if we extend that power law of 0.6 all the way out to 0,
Yes.
we're going to get a number like 3-to-1.
I was going to say, yes, very good. Uh-huh.
Yeah.
Okay. So that's a limit.
Yes.
Okay.
And we still don't know what the low mass cutoff is, so that's TBD. But why don't we scroll? And there's an appendix after all of this, which is showing Appendix A is describing all of the follow-up spectra and photometry and parallaxes that we got on the new discoveries from the citizen scientists of backyard worlds. And that was just to flesh out better the new discoveries in brown dwarf space.
Yes.
And I won't go into that in any detail at all here, but you're free to look at it if you wish. But Appendix B is the one we put in just for fun.
Oh, fun. Okay. Good.
And Appendix B is saying, and I've seen this question asked a few times online by, armchair scientists and maybe some professionals too, saying, what is the closest star in each constellation? You thought, why would anybody want to know that? Well, if you think about Proxima Centauri, we know that it's the closest star to the sun.
Yes.
It's called Proxima Centauri, Proxima because it's the closest, right? But if you look at it grammatically, Proxima Centauri really means the closest of Centaurus.
Yes.
Which has led people online to say, well, what's the closest one in the other 87 constellations?
Gotcha.
I kind of want to know just for curiosity's sake.
Gotcha.
So what we did with this was said, okay, what are they?
Oh, here we go.
So this last table here is just showing what the Proximas, if you will, would be in each of the other constellations.
Correct. I get you. This is cool. This is fun. Okay.
And there are some of those where, first of all, you only have to go out to about 15 parsecs to have a closest in each one of the constellations. I was worried that there are going to be some itty bitty constellations there.
Yeah.
Have any representatives within 20 parsecs, but there aren't.
Nice.
And there are a few where the closest object within that constellation is a white dwarf that you'll never be able to see by eyes. It's too faint of a brown dwarf.
Oh, very cool.
And that's it. That's the bottom of the paper.
That.
Except for the references, we've almost made it to page 93.
Then we go 85, and then we got 8 pages of references there. Very awesome. Very awesome. Davey, I want to thank you so much for walking us through this awesome article, APJ supplement article. Very cool.
You're welcome.
I would say it's a beautiful summary of 3 years of work. Very cool. And so that'll lead me then. You hinted at it a couple times, and so let me just ask. And I don't want to volunteer the next 3 years of your life, but let me just ask: where do you think we go from here, given the published article? What would be some of the next immediate steps that one would want to take to improve the catalog, improve the mass estimates, improve the initial mass function?
I think there are 3 things. So the first is one that I'm very curious about and would like to be a part of myself, and that is pushing the cold objects further. So we really need to have a survey that will look at the colder nearby objects and discover those for the first time. And the right mission, I think, to do that's coming online soon will be NEO Surveyor. Now that is a NASA planetary mission. It's actually looking for near Earth objects to see if any rocks we don't know about that could potentially smash into the Earth.
But they got to go cold. That's the point.
They got to go cold to find these, and that's perfect for us because we got to go cold too.
So it's serendipitous science.
So it's going to be astrophysics that a planetary mission can do, essentially.
Yeah, it's almost like something like TESS or those things, right? Where the primary is looking for planets, but you also happen to get some fantastic photometry stars, right? But
lots of ancillary science you can do, and some of top notch.
That's one. Cold.
That's one. Another is I'm really worried about those mass estimates in the M-dwarf regime. I think those could be cleaned up now. And since we have these time domain surveys coming online, and astronomy is going to be all about these gigantic data sets in the next decade, right?
Yes.
we're going to be able to identify a lot of M dwarfs within, a few, 200 parsecs or something of the sun. So we could use those to actually get direct mass measurements and clean up that whole estimate part in the M dwarf regime here. And that will help get rid of all those little kinks and wiggles that we think are artificial.
Right.
Then the third thing I would say is we've got lots more work to do on those things that we think have a hidden companion that we don't really know what the companion is yet. So if we can help clean those up, then I think those spikes you saw in the blue histogram and the money plot will start to go down because we'll get the better estimates for those guys.
Right. Very
So those are the three things.
good. That's a short, sweet, clean future. I love it. Very good. Well, I really look forward to seeing this our knowledge of the IMF and stars in the nearest 20 parsecs or greater eventually if we get there. Be really exciting to see this develop. It's really cool. And I do want to congratulate you and the entire team. I know how hard it is to put together a manuscript of this size. So congratulations.
Thank you very much. Yes.
Very cool. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we'll see you on the next one. Bye-bye.
Bye, everybody.